For our final junior design project, we chose the telemetry project. This project required our group to design, build, and test an enclosed system capable of transmitting its current position, battery life, and temperature to a base station up to half a mile away. The system must be robust, accurate, and capable of operating for long periods of time in cold, wet, or hot climates. The project was developed over the course of 8 weeks, with the final testing being completed week 9. The system is expected to log and transmit data for at least 12 hours on a single charge. Although we were able to prove mathematically that our project was capable of operating for nearly 22 hours on a single charge, due to a battery malfunction, we were unable to achieve the full 12-hour time lapse. The system is expected to log GPS data with at least a 10-meter accuracy. Using 2 USGS markers as fixed points on the map, we can see that our system achieved this requirement. The system is expected to fulfill a few different robustness tests. The first is that it must be capable of surviving 5 drops from a height of 3 feet or above. The first test, as seen here, didn't go quite as planned. Fortunately, we were able to salvage the enclosure and then reinforce it. Here we can see that it can now survive from heights above 3 feet.
Oh, it's rattling. Does it still work?
It's, have to wait 15 seconds.
Oh, 15 suspenseful seconds.
It's not working.
It's not working. Oh, it's working!
It's working.
Yes!
Look at that. Battery life 67%. Yeah, it's working.
The second requirement is that it must be able to function in extreme cold or hot environments. Here we see the system being placed in a freezer that is approximately negative 10 degrees Celsius. Once we take the system out of the freezer, it continues to function normally. Similarly, we put the system into an oven operating at 85 degrees Celsius. Once we take the system out, it still functions as it had before. Finally, the system is expected to operate while submerged in up to 1 centimeter of water. Here we can see Steven, our enclosure specialist, taking pride in his work as he submerges the entirety of our final project in water, clearing this requirement by miles. The system is expected to transmit its measurements over a distance of half a mile with at least 95% accuracy over the course of an hour. Here we can see a half mile measured out in Google Maps. The right side is where the base station was standing, while the left location was where the system was located. This is the recorded footage from the base station over the course of the hour. As you can see, it was able to receive data even as the system moves further or closer to the base station. The system is expected to display all the data inside of MATLAB. The overlay must be professional and accurately display the data. Here we can see the interface that Jared, our MATLAB specialist, created. It shows not only the real-time GPS position of the system through Google Maps, but it provides the users with the ability to zoom in, zoom out, see the world through Street View, and move about within the Street View. The interface also tells us the temperature of the system, as well as the current battery life. If the base station does not receive any signal from the system, it will display a message telling the user the system is out of range. The system's block diagram has been refined a couple times throughout the project. This is the final version. Here we can see the Teensy microcontroller is the primary control block inside of the system. It is responsible for controlling the GPS, temperature, and RF communication data inside the system. Every other component, besides the base station components, communicates or connects to the Teensy.
We chose the Adafruit Ultimate GPS module due to its already written Arduino library, as well as its versatility and power as a GPS unit. We knew going into the project that a good GPS was going to make or break our system, so we invested in a GPS that was praised for its reliability. The Teensy was chosen for its small size, modularity, low power consumption, and the number of input and output pins the board contains. It also has a large amount of onboard memory and is capable of consistently driving the voltages required for our project. The Uno was selected for use in the base station because of its reliability and ease of use. The battery was determined by observing our active power consumption and the size of our enclosure. Taking both of these factors into account, along with the requirement for the system to function for up to 12 hours in a single charge, we settled on a 6-volt battery with a 2.2 amp hour capacity. The RF transceivers used for this project are RFM95 modules by Seed Studio. They come equipped with antennas that are already capable of reaching the distances required by the system. These modules also already have an Arduino library written for them, which made getting them to communicate between the Uno and the Teensy much easier than originally anticipated. The enclosure we used was made of 5mm polycarbonate. We originally intended to use steel for our enclosure, but opted for polycarbonate instead to allow the RF and GPS antennas to be sealed inside the enclosure. Originally, we planned on having an antenna that extruded from the enclosure itself, but due to our GPS module using a built-in flat antenna, we were required to use a material that allowed signals to easily pass through while maintaining robustness. The PCB designed for this project was completed early on in the development cycle. Its primary use is to connect each of the components together, as well as to ensure that each component stays held into place. The GPS is soldered directly onto the PCB, while the Teensy is placed on by way of female and male header pins. This allows for quick fixes and adjustments to the Teensy module, given that it is the most crucial part of the system. Finally, the PCB includes circuitry for the power, LED output, and temperature components required by the project.
Unlike other Arduino boards, the Teensy requires additional software on top of the Arduino IDE in order to program it. This caused some problems early on in our project when testing the RF modules, but we were able to quickly figure it out as we used it more. The library included for the RF modules uses a server and client method of communication. We defined our base station as the client and our system as the server. This way, the client can ask for data, which the server can then send on command. Here we can see the C struct used to package and send the system's data. This struct is identical on both the Teensy and the Uno, which allows for easy packaging and unpacking of the data. The Adafruit Ultimate GPS also comes with its own pre-written Arduino library. It will automatically boot the GPS chip, sync it with multiple satellites, and then provide the Teensy with the raw data in a convenient form that is easy to plug into our C struct. There's also a lot of additional data provided by the GPS that we leave behind on the Teensy, such as details about the satellites, data quality statistics, and also date and time information. The temperature and battery data are obtained through two simple pieces of code. The temperature is found by reading an analog voltage and then performing a simple voltage divider calculation to find the resistance across the thermistor, a component used for measuring temperature. The battery percentage and LED battery indicator output is determined in a similar way. The Teensy reads an analog voltage from one of its pins and then performs a calculation to determine the percentage of battery remaining. We use this percentage in a simple if-else tree to drive the respective LEDs when a button on the device is pushed. Using an API provided by Google, we are able to show in real time the satellite and street view of the coordinates provided by our system. Our system also displays the temperature, battery percentage, and raw coordinates. Our MATLAB display also provides controls for changing the type of Google Maps shown changing the zoom level of the Google map, and changing the direction the user faces in Google Street View.
In conclusion, our junior design project went more smoothly than anticipated. Although there were road bumps along the way, each member of the team carried their respective area's weight and helped push the team forward through each of the weeks. Our project was able to fulfill each of the requirements and met the expectations of the class. Thank you for taking the time to watch our video.